I've long been a consumer of decision theory and try to push it towards some new directions that I think important for applications. This is going to be very much taking decision theory out for a spin and actually showing how I think it adds some substantive insights and to think about some questions that in substantive economics that with a little bit different perspective than is out there in the related literatures. So I want to be focusing on growth rate uncertainty, and I'm going to do this in the context of a couple different settings. One is a market setting, and one is a policy setting. I think growth rate uncertainty is one of the big motivators I've had for thinking about uncertainty, because it's really hard to measure the growth rates with great accuracy and great confidence, especially as you can try to compound them over time. On the other hand, there's lots of evidence, especially from the macro finance literature, that growth rate uncertainty can have potentially big consequences for valuation. So sources of uncertainty that I think are difficult to quantify probabilistically could include things like so-called secular stagnation. There's been debates among leading macroeconomists whether we're, after the financial crisis, whether we're permanently stuck in a rut or whether it was going to be something transitory which we grow out of. There's lots of discussions these days about the so-called digital economy, and then there's speculations about how important that's going to be in terms of future growth and development. And of course, the example we're all unfortunately experiencing is the pandemics. Epidemiologists and economists explore both short-term and long-term implications of pandemics. Finally, geoscientists and environmental economists make conjectures about how climate change could alter economic opportunities. So in all these cases, one can write down fully specified probabilistic models, but I think it's a fairly contrived exercise to do so. So where does uncertainty emerge? So I've been kind of a committed model builder of economic dynamics. I like models. I like them for quantitative purposes. What do I see their role as? So I view quantitative models as a form of quantitative storytelling. But then you want to tell these stories, you have multiple models, which means multiple stories. Each story kind of gives you an interpretation of the data with a potential policy prescription or the like, but then we may be unsure about which is the right one. And at the same time, we also suspect all these models, as consistent with Massimo's earlier discussions, these are like models or simplifications or abstractions. They allow us to provide these transparent interpretations, but we don't really want to claim that they're like fully correct. They're going to miss along some dimensions, and we're not quite sure where. So, consistent with some language that Massimo used, we're going to be thinking about risk. Each of these models we write down, and it has random impulses to it, which require certain numerical inputs, and then we kind of solve out how the model responses to those random inputs. Those random impulses. Ambiguity, we have multiple models, each give rise to multiple stories with different implications. Finally, misspecification, each model is an abstraction. It's not intended to be a complete description of reality. If it were such, it would probably not be terribly useful. So I'm very much in the same type of spirit as say Massimo's talk. So let me try two quotes. One is from Keynes and the other is from Knight. I guess we had discussions of their contributions in previous days. Keynes, uncertainty must be taken in the sense to be radically different from the familiar notion of risk, and arguing that should really be separated. From Knight, from Keynes, we say that we have to rule only the vaguest idea of any but the most direct consequences of our act. Our knowledge of the future is fluctuating, vague, and uncertain. So I think that's been the motivation of this conference. It's also been in part the motivation of this research. I don't have any illusion that either Keynes or Knight, were they alive today, would be embracing this as addressing the answer to their challenges. But at the same time, I think it's a useful way to go. So I'm going to be using decision theory that has this, that's kind of dynamic extensions of some of the ideas that Massimo put out there. There's going to be families of structured models. Okay? They're going to confront unknown parameters and potentially parameters that change over time. In the first example I'm going to be talking about, it's going to be a market economy, but it's going to be made simplified computationally by the fact that I can solve it as a social planner's problem and then deduce market prices from the solution of that planner's problem. I'm going to be doing this in continuous time. It's going to facilitate certain characterizations, but I'm going to be using kind of a framework here of that Chen and Epstein kind of built from Gilboa-Schmeiler in this dynamic continuous time setting. That's going to be the way I'm going to handle structured models. There's going to be also these families of so-called unstructured models, ones in which I don't pretend to have structured interpretations to, that will potentially confront model misspecification. Here I will use the kind of so-called robust control, adapted and modified from earlier work that Tom and I've done, extracted with a big input from the robust control literature. Now you might ask, why don't you lump these two things together? Well, it turns out that in dynamic settings, we know from both Epstein and Schneider and Chen and Epstein, they have to constrain things to be this so-called rectangular specification. And I won't get into this today, but there's a recently published paper by Self and Sargent and Jett that discusses this issue, showing that indeed that type of restriction puts off the table any type of entropic notions of model misspecification. And so that alone mathematically constrains a set of models. And we view it as potentially interesting as a way to kind of build structured models, but not as a way to deal with model misspecification. Okay, so the formal approach here, computationally, we're just solve as a two-player zero-sum differential game. We're writing stochastic differential equations for state evolution. This could be mostly, for the first example, where there's going to be Brownian discussion, Brownian risk for the climate change example I'm going to talk about later. There'll be Poisson components to it. One player is a fictitious player engaged in maximizing social well-being, and the other investigates the adverse consequences of uncertainty about probabilistic inputs through minimization. We will be using relative entropy to limit or bound probabilistic uncertainty, and of both types in this case. And we'll be using numerical PDE methods along with some extra twist for the computations. So in this continuous time setup, and in a general dynamic setups, it's very handy to think about alternative probabilities through martingales. The one exception to this was the very interesting work of Peng and others that's kind of pushes us away from this absolute continuity. There's things I could say about that, but that's not part of the examples I'm talking about, so I'll put those issues to the side. So let me just, for notation, in this continuous time Brownian setup, there's this very nice, we kind of learn this from financial engineering. There's a very nice characterization that says that changes in probabilities that are absolutely continuous over any finite horizon correspond to drift distortions, Kirsanov type theory. So we're going to have different versions of this. We'll have the structured version, which will be a more narrowly confined set, and an unstructured version, both of which we can map to these so-called drift distortions. And as I say, focusing on drift distortions is what we do here. I'm very much open and in other work investigating the kind of what happens with changes in volatility. So I'm going to put down a very simple illustration. It's going to be an incredibly stylized macro model with growth rate uncertainty. This has been used as a kind of an important example in the macro finance literature under the heading of long run risk, and we want to think about it as something other than long run risk. The long run risk literature, which I'm sure most of you probably are not inside of, has this interesting origins to it. It says that, well, this goes back to Bonsall and Yaron's work. It says, we're going to take a rational expectations model in which investors have full confidence in probabilities of everything. We're going to impose long run risk. It concedes in their initial paper, it may be hard to tease out from the data, but then they show that if investors are committed to that long run risk, it has important consequences for pricing, and therefore they embrace it. But they don't embrace it based on primitive evidence. Now, subsequently, there's been some work challenging that, but I think the primitive evidence remains weak. So to me, that type of defense was not terribly compelling. Where do investors get the confidence from? So I'm going to start off with an initial model. There's going to be it's going to be two equations. Think of YT as just a proxy for the macroeconomy expressed in logarithms: log consumption, log capital, log output. There's going to be Brownian increments. There's going to be two of them here. There's the so-called DW components. The long run risk literature itself has stochastic volatility, but what I want to be doing, I'm going to put that to the side here because I want to show that I can induce fluctuations in valuations without putting it in exogenously through stochastic volatility. Then there's going to be this second process here, the so-called ZT process. It's going to involve what is a continuous time version of an Ornstein-Uhlenbeck process. Let's say it's basically a continuous time first order autoregression. That's going to be the so-called long run risk. That's shifting around the growth rate in the macroeconomy in ways that are not fully predictable. So then we have these coefficients are going to be of key interest to me. Two of them in particular are the paper this is built on explores higher dimensional versions of this, but for today I might be thinking about uncertainty about this coefficient beta y and beta z, and that's going to be the form of the structured uncertainty here. Those how exposed is the macroeconomy to this long run risk factor, and then how persistent is that long run risk factor. So if beta hat z is very close to zero, that corresponds to lots of persistence and input. And when it's positive and substantially away from zero, then there's not much persistence. And that's the uncertainty here. Okay, so we can represent these restricted models then by the so-called drift space, changes in drift, and this just gives you the mapping for doing it. I write down some other model with some different coefficients, and this just shows you how to map that back into a change in the drift. So as changes in drift can capture this coefficient uncertainty in this model. Now, I'm not going to go into great detail to this slide here, but there's different ways one can restrict the structured models. We actually use relative entropy there, but as I indicated at the outset of my talk, relative entropy in its most general footing is not compatible with this so-called rectangularity property. This rectangularity property of Chen and Epstein, one imposes restrictions instant by instant. So there, what we do is we constrain the local evolution of say relative entropy. But there's other ways to construct these structured models. But here we do it through local evolution. Formally, we write down corresponding Feynman-Kak equations and look at those and then look at from those equations, limit the local properties of relative entropy. So we are using relative entropy here for the structured models, but in a much more constraining way. So the usual rational expectation story here announces a point. It says investors all agree on what the two coefficients are, beta y and beta z. We're going to be exploring ambiguity sets here. Okay? So an example would be this bigger set here, and then there's a potentially larger set, which is which one could explore as well. So these look like what econometricians or statisticians think are confidence sets, but what they really are for us are these ambiguity sets. Investors, instead of committing to a point here, are going to commit themselves to being somewhere in this region. So we discuss possibilities of instead constraining Bayesian posteriors over things. Here we're going to go all the way to explore the entire region. So at any point in time, investors are going to consider parameters, these beta parameters somewhere inside the set, either the smaller set or the bigger set. I'll just be focusing more on the smaller set today. But so basically, relative to the existing literature, we're taking a point and replacing it by a set, and that's what the investors come into the decision problem with. At the same time, they want to allow the model to be misspecified. So time variation in parameters is allowed here, provided you stay inside this set. Now, when applied people write down time varying parameter models, they always make up probabilities about how they evolve over time. But those are often contrived as well. And so here we eliminate the we dispense with those probabilistic specifications. So confronting misspecification, we're using a discounted version of say, relative entropy. Here it's because of the, we're looking at the relative entropy of the structure, of the unstructured models relative to the structured model. Now, in this continuous time diffusion context, it boils down to looking at the drift distortions, the squared drift distortions divided by 2, and then we'll evaluate the expectation under the potentially unstructured, under this alternative unstructured model. Okay. So this is how we're going to limit forms of misspecification. This is all very tractable. We're adding some, we're adding some extra penalization term to an HJV equation for a fictitious social planner. So to accommodate misspecification, we minimize U for a given S. To accommodate model ambiguity, we then minimize over S. And then the nice part of all this theory is the fact that when it comes to doing valuation, it's the solution to the minimization part of the max-min problem that tells you how to do valuation. And so not only does it inform us, not only does it help us to enforce the concerns about ambiguity and misspecification, it actually, we can take it one step further. That's what leads to decentralized prices, and that could be shown. So let me, there's 2 different evolution equations here. Let me focus on the persistent part and the persistence part of it. The trade-off here is, of course, very important, but let me just focus on this. And so I've got a couple different lines here. I've got a baseline here. The baseline, remember that Ornstein-Uhlenbeck process had linear dynamics with a negative slope. The negative slope is what's needed to pull yourself towards the center of the distribution, mean reversion. We're imposing mean reversion. Of course, the growth rate in the economy is not 0. Here, I just recentered things to be 0 here. There's an additional constant term shifting around the growth rate of the overall economy. And the baseline model just has you sit along the black line. That was that kind of rectangular point in which we had inside the ambiguity set. That's this. Now what happens is I introduce that ambiguity set of models, okay? And then I'm having this decision maker not only figure out what the optimal choice of consumption and investment is, but also along the way doing this minimization. And here the red line is under a purely structured case. There's no concerns about model misspecification. And what happens here is that you get a steeper slope on one side and a flatter slope on the other side. You've taken what was a linear baseline model, and for purposes of valuation, you've just stuck in a nonlinear model that a time series econometrician or statistician would recognize as basically a threshold autoregression. The threshold autoregression is not because that's what you believe is generating the data. That's what you use to implement a conservative adjustment. Now, why is there a threshold model here? What's going on with the slopes? There's a pretty simple intuition behind this, and let me explain that. Imagine you're sitting here at a growth state that's better than average. So we're to the right of 0 here. You've got alternative models on the table, and you're going to ask, what models do I like and what ones do I fear in terms of persistence? Well, if the growth is good, the models I like are ones with high persistence. Let the good times roll. Let's just keep going with the good times. What you fear is the lack of persistence. Okay? A lack of persistence means that slope coefficient in the dynamic evolution for the persistence must be bigger, more mean reversion. That's what's driving this. Now change the story to a bad growth state. Ask yourself, in a bad growth state, what models do you like and what models would you fear? Well, the one you would fear is being stuck in a rut. Persistence is bad news if you're sitting in a bad growth state. So the lack of persistence is what you'd like, because that means you're going to escape out of this bad growth regime. You're more likely to escape out of it quickly. So this minimization property leads to a flatter slope to the left. So it's what you've taken as linear dynamics, and for the purposes of valuation, replaced them by this nonlinear dynamics. And this can be a source of kind of nonlinearity showing up in valuation, even though it's not may not be all that evident in the primitive data. And so it says that we're getting kind of fluctuations in valuations based on the state of the economy because of this differing views of what are good and bad models. So I think that's an interesting mechanism coming out of this broad notions of uncertainty aversion. Let me add a model misspecification here. Model misspecification leaves that kind of kink. It smooths it over a little bit and does a downward shift. These misspecification concerns kind of ultimately go for the very long run impacts, and so they kind of lead to more closer to parallel downward shifts. And so that that adds on to this. Okay, so let's just see how growth rate compounds here. I begin with the original baseline economy. What I've reported here are the 0.1 and 0.9 deciles. If I activate the ambiguity concerns, I shift downwards like this. I have that's the more conservative adjustment, and then if I add on the misspecification, it's a further adjustment downwards, as given by the blue cone-shaped region. So I expect this because of compounding effects. I expect these quantiles to increase. It's just that they now get this extra tilt because of these conservative adjustments being made through the aversion, ambiguity aversion, and the misspecification aversion. Okay, so what have we received with this example? A tractable approach for confronting uncertainty. A mechanism for inducing fluctuations in asset prices that isn't just imposed exogenously. There's like stochastic volatility. And the mechanism has a pretty simple story behind it. Investors fear persistence in bad times, and they fear the lack of it in good times. Investors' perspective on the set of models changes depending upon the state of the economy. And so that's what underlies the first example. Let me next talk about this, lead up to a discussion of economic policy and uncertainty. I've been often, Hayek wrote this essay after he won the Nobel Prize. It's kind of an interesting essay because Hayek wins the Nobel Prize. He shares it with Myrdal, and he writes this essay questioning to what extent economics is really a science. So after winning the Nobel Prize in economic sciences, he writes an essay that kind of challenges whether, to the extent that it is. Now, Hayek's very, very hard on econometrics, dismisses it as not a very productive enterprise. So I don't agree with all aspects of this of his essay, but there's this quote here that I think is worth thinking hard about. Even if true scientists should recognize the limits of studying human behavior, as long as the public has expectations, there will be people who pretend or believe they can do more to meet popular demand than was what really in their power. So this means if you really want to do quantitative policy analysis, how should we acknowledge the limits to our understanding? There's this kind of simplistic notion that to convince people, you've got to project yourselves with great overconfidence. Multiple economists do this. Their overconfidence conflicts with each other, and then the whole enterprise gets dismissed as being as being somewhat shaky because of that projected overconfidence. There's very clear fear in policymaking settings about acknowledging too much uncertainty, and I think it's really important we figure out constructive ways to get around that fear. Anyway, I'm going to turn to climate change here, and I'm going to refer to, and I'm going to use a construct called the social cost of carbon. This construct, its meanings and targets and measurement differ across applications, but I'm going to use a well-posed version as an analytical tool to assess the impact of uncertainty. And here's what's going to be for me. I'm going to put a fictitious social planner on the table. Now we're dealing with an economy where there's an externality. Carbon emissions alter the climate, that in turn impacts economic opportunities and social well-being. Markets in this setting will not internalize that, and so that opens the door for policy intervention, reflected by the social marginal rate of substitution of consumption and say emissions and carbon emissions. That's the social cost of carbon. It would support hypothetically Pigovian taxations in terms of designing a tax on carbon emissions. It's the kind of price that corrects this externality, and we want to figure out how responsive that is to uncertainty. So this can be by way of an example. Here, instead of using the kind of using this kind of Chen-Epstein-Schneider approach, we're going to be using a version that's more of like a smooth ambiguity version, extended to continuous time by myself and Yao, but it's basically a continuous time version of the Klebanov-Baranacci-Mukherjee smooth ambiguity model. The ambiguity is going to be over local specifications of the state dynamics. This can be and that's going to be the way, and then we impose our structure through that. And then there's going to be, but it's going to be handy for us to continue this notion of a probability representing things by a distorted probability distribution, just as we did before. That's very, very handy for valuation purposes. Now, for some smooth ambiguity specifications, and this is something that Serge and I pointed out a while ago, there's this kind of equivalence between smooth ambiguity and robust choice of priors. And so you've got this prior over sets of models, and you're going to jiggle that around, and you're going to jiggle around using a relative entropy type penalization, and that can give rise to a special case of smooth ambiguity, and that's what we'll be using here. You can add on additional adjustments for model misspecification, comparable to what I was doing before, and in particular, we'll be thinking about this in the context of damage functions, so-called damage, which I'll talk a little bit more about subsequently. Now, what's handy about this in terms of policy analysis is we can take a model that's got lots of different pieces to it, but and we can use decision theory, this type of decision theory, to boil down this sensitivity concerns down to one or two parameters. One governing, say, model ambiguity, another governing model misspecification. Now, of course, decision theory doesn't tell us how to set those preference parameters, but at the very least, we're now like, the researchers is now kind of scoping out these much lower dimensional characterizations of the rules of uncertainty here for the purposes of decision making, which I think is can be really very revealing. So I find this way to doing a sensitivity. I find this use of decision theory as a way to do a sensitivity analysis to be a very fruitful tool for doing applied research. So I'm going to put on the table here the following: the first climate change uncertainty. So what we've done here is we've taken I boiled out the climate models out there. We simply cannot use. They're very, very complicated. In fact, climate scientists themselves are often figuring out ways to simplify their their implications because of their big complexity. They can take a long time to even solve. But we want to input. But we want to take inputs, and we're going to borrow on some evidence coming out of the climate science where they run these so-called pulse experiments. Now, what a pulse experiment is you take a big model, you give a standardized pulse to a bunch of them, and then you kind of and say emissions pulse, and then you kind of go through and you trace out their consequences. Now, the climate dynamics have multiple pieces to them. One is the mapping of emissions to carbon in the atmosphere. The other is a mapping of carbon in the atmosphere to temperature. And indeed, there's uncertainty about both of those pieces. What's reported here is like the convolution of those two different pieces. And so I'll take all the different models. I think the model configurations here are like well over around 140 or so different models. For each of those models, I'm going to trace out what the response is to an emissions pulse over a 100-year time period. Okay? And so what you'll see is that what I'm reporting here are the quantiles, 0.90, 67, 33, and 0.10. The models all have this noted feature that, yes, there's some initial buildup really quickly, but then things flatten out, and there's a very flat response after that. That says that these emissions, which you put in the atmosphere, from a standpoint of economists, have very, very long-lasting inputs. Now time. What's long for an economist and what's long for a geoscientist is really quite different as they build models that are supposed to work over many, many centuries. And we're lucky to have models that we trust over multiple decades. But anyway, we're tracing out these pulse responses over a 100-year period. In particular, we're interested in kind of where this levels off here. And so you'll see there's a fair bit of heterogeneity here. The upper and lower envelopes here capture all the models, and then I've told you where the 10 percentile is and where the 90 percentile is of these. We're going to load in these outcomes as a type of model uncertainty into our analysis. Now, we're going to take all these model configurations and treat them, quote, equally. We'll assign them each weight, say 1 over 140 or whatever the precise number is. We're going to weight them all the same. Now, there's no reason why that we should be fully committed to that weighting. We're going to want to jiggle around those weights and see what the consequences of those are. So this is the climate side uncertainty. There's a corresponding economic side of the uncertainty, and I'm going to adopt a convenient simplification here using damage functions that kind of map temperature anomalies into economic damages. What's known about this at the aggregate is pretty sparse. There's a lot known about kind of much more granular level of damages, but what's known at the more aggregate level is arguably quite crude information. And there's lots of heterogeneity in terms of what people think about those damages might be. So what I'm reporting here is a damage function. Kind of think of this as the fraction of productive capacity of the economy that's destroyed by temperature anomalies. Here, the damage functions I'm looking at are all going to stay the same until we hit 2 degrees, and then they'll start splitting. People think of 2 degrees as places where big dramatic things might start happening. The red line is the low damages, and that's kind of calibrated using some work of Nordhaus. The high damages is more motivated by some of Weitzman's arguments that yes, there's because of some form of model uncertainty, we should perhaps have bigger tails. Though Weitzman doesn't really deliver it formally in terms of the class of climate models. For us, we're just going to entertain a larger high damage models. And then if you look at some of the discussions, especially coming out of climate literature, but also among economists, there's an argument for doing carbon budgeting that says that, well, we should only allow the temperature to go up to 2 degrees and no more. And then we should just figure out how to allocate emissions over time in order that we don't cross that barrier. Instead of imposing a carbon budget, we're going to take a smoother response, trying to allow for some forms of adaptation and the like, and have a green line here of extreme damages. I'm going to do things like impose probabilities across these, equally likely probabilities as starting points, but then kind of see how sensitive calculations are to those probabilistic specifications. So we took, I'm sparing you the details, but a fairly simplified climate change economic model here. And then we took the original set of a histogram for that kind of mapped those responses I talked about. That's given by the red line, by this red histogram, by the red version of the histogram. And then I've imposed a type of smooth ambiguity parameter such that the outcome of this changes to the blue one. Now that's a choice of parameter. If I change that penalization parameter more or less, then I could make this adjustment more or less. But for this given configuration, you're then the planner to make this conservative adjustment by shifting probabilities towards the right here, making the system more sensitive to emissions. So the point is, we have a pretty wide histogram to begin with, and there's ways to. But treating all models equally just an arbitrary starting point. And so this is a way to explore the consequences of this. Of course, you might bring in more experts. They may have stronger opinions on what are good and bad models. We might start with different baseline priors and the like. Now, the way I'm going to deal with these damages, and I should have been clear about this before, with these different damage functions. Let me just go back 2 slides. How I'm going to treat this. So this is a model where you can't learn, it's very hard to learn anything here until we reach extreme temperatures. The first work we did on the subject is we did calculations with presuming you never learn the damage functions. That led to some really strong uncertainty impacts, and I was concerned that we were greatly exaggerating them. What we're doing here is we're going to say at the point where the things separate, you're going to at that point know what the damage function is, but before that you don't. You have ambiguity over the damage function prior to that. And then we're going to solve this as kind of a PDE system in which we've imposed, we use kind of a robust adjusted or a continuation value that looks across these different different type of value functions associated with the different damage specifications. And then we're solving our PDE subject to appropriately chosen boundary conditions that make uncertainty adjustments. Now, in general, you want to put explicit learning on here. Exactly what evidence you do use to learn about damage functions and the like is not entirely clear, but yes, actively integrating learning formally, and this would be useful. There's lots of people will have argued that the learning rate now is very, very slow. But once we hit extreme damages, of course, that could change dramatically. So anyway, that's to the side. So for this particular calibration, we start off with probabilities a third, a third, a third. As we move towards this threshold of 2 degrees, what happens is you start tilting probabilities more in this in order to implement this these robust and ambiguity averse adjustments. You take the extreme damage model and move it up from to starting from 0.4, and then eventually, as you get closer and closer to this threshold, then you even bump it up more here to 0.5. The low damage model, you start off at somewhat less than 0.33 and then push it downwards. I would not really necessarily describe these as dramatic shifts in those probabilities, but by changing parameters, I can make these things bigger or smaller. Okay. So with these parameter configurations, then I can show you what happens to the social cost of carbon. What I'm going to do is I'm going to show you the total amount, the total social cost of carbon here. This increases over time over this 100-year period. This is the social cost along the socially optimal trajectory. So this wouldn't be under current emission scenarios or business as usual. This is under the solutions to a planner's problem. So there's already so the planner is trying being prudent in terms of the how emissions are playing out over time. In these calculations, about 20% of that gets accounted for by the uncertainty adjustment. And the way we actually do this is we do a comparison, and we do the valuation under those minimizing probabilities, and that gives us the kind of correct evaluation. Then we say, well, suppose we hadn't used those probabilities. Suppose we go back and just use the baseline probabilities, redo the same calculation, and that would give us a line down here. And so this is like a 20% adjustment. Now we've used in subsequent work, we've gone a step further. We said, well, of this uncertainty adjustment, is it coming from damages? Is it coming from temperature? Is it coming from carbon dynamics? What we can show is that the damage specifications I've given you is the biggest contributor of the three, but there's these impacts of uncertainty are multiplicative in nature. And what happens is they get reinforced. So the temperature dynamics alone doesn't do much, but once you interact it with damage dynamics, that then becomes much more prominent. So talking about these in isolation is not so useful in these setups because the multiplicative nature, there's important interactions that take place. And that's kind of an interesting part of doing this uncertainty analysis. Taking inventory, so the social cost of carbon could be magnified by a prudent social planner who does not have full confidence. The planner implements the uncertainty aversion by replacing baseline probabilities with these kind of adjusted counterparts. So these probabilities that come out of the minimization problem help us think about valuation as well, and that's a very useful tool for us. These adjusted probabilities provide a revealing assessment of the magnitude of the aversion. Here's some related papers I won't bore you with. With that, I will stop.
Thank you very much, Lars, for this enlightening talk. And the floor is open for questions now. We have some time for questions, so please go ahead. I see no questions yet, so maybe I will ask Lars. I'm not quite.
Sam raised his hand, I think, too. So.
Oh yeah. Go ahead, Adam. No.
Oh, can I jump in?
It's fine.
I was wondering, in your social planner problem, can you say qualitatively, is the planner more or less conservative with regards to the amount of carbon released, given their uncertainties?
Oh, more. Yeah. I could show you plots. Yeah, no, there's movements in the uncertainty makes the planner emit much less carbon, kind of uniformly over time in the setup. So the social cost of carbon calculations I did help fix the amount of emissions that they at the prudent planner optimum, but then when you also compute it under ambiguity, under neutrality versus ambiguity, there's the depletion of the emissions trajectory is reduced. Unfortunately, I don't have the plots for that right here, but yes, I should have included those.
Okay, there is a question from Nan Lee. Nan, would you like to ask your question?
Hi, Lars. Nice to see you here. And I actually have a question about this calculation of this growth uncertainty versus and also this question I think applicable for the climate change. So in both of these models, you didn't consider this ambiguity towards the volatility. It's all about these means. So I'm wondering what happens if we are concerned with this uncertainty regarding the volatility, and we can probably use Professor Peng Shige's G-normal type of the calculation to compute what exactly would be the impact of this ambiguity towards the volatility.
Yeah. So actually, he and I are supposed to be writing a paper in this subject that I've been the holdup on, but indeed it's within this setup. So we can build in the this type of analysis into our structured uncertainty components here and put volatility on the table. We're not relying on absolute continuity there in any essential way there, and so it's possible to integrate it there.
Okay, Lars, there are two more questions. I will read one of them and I will ask attendee to ask the other one. So the first question comes from Berend Roda, and he asks you to please elaborate on relaxing rectangularity. Is there any alternative axiom for that?
Oh yes, relaxing rectangularity, yes, okay. This is like a separate talk, I think, unfortunately. So yes, we show examples in our paper that we think that rectangularity and model misspecification in these dynamic setups just don't jive very well, and that's why it's important for us to push beyond that to this variational preference setup, and relieves us of some of the what I view as rather extreme restrictions coming out of rectangularity. So I think the rectangularity is a very nice contribution because it shows. It shows how to merge dynamic consistency with a Gilboa-Schmeidler setup. But for us, it also opens the door to considering other forms of preference specifications that captured by the variational preferences. Now, what smooth ambiguity is a different way to go here, and there's issues there, and that's what we use in the separate setup. There we use smooth ambiguity by penalizing things over priors or posteriors, and so it's more of a smooth adjustment in that sense. That doesn't get us to model misspecification because thereby, by construction, you've imposed a structure over models in the smooth ambiguity setup. So again, I think there's important scope for model misspecification here as well.
Thank you. Thank you, Lars. One more question from Philip Eisenhower. Philip, go ahead, please.
Yeah. Right. Thank you very much for the presentation. I just have one question. So in the example that you gave from the social cost of carbon literature, there you had the uncertainty coming in through an ensemble of different calibrated models, right? So yeah. in our case, what we are working on structural microeconometric models, and what we're trying to do there is do this idea of the sensitivity analysis of policy rankings with respect to alternative decision criteria, taking into account the uncertainty in the form of the remaining parametric uncertainty. And we're exploring some ideas there on how to incorporate this properly. And I was just wondering if you have any thoughts about how to deal with the parametric uncertainty within models, just taking a single one and then accounting for the uncertainty in the counterfactual policy predictions, or any references that you think can be helpful there.
Okay, so
thank you very much.
The first example I gave was one of parameter uncertainty. Now we didn't do policy there. That was a case where it was a fictitious planner was doing the adjustments there instead of a and then showed how to decentralize the economy. But there's really although the climate models we talk at here, we didn't load in parameter uncertainty. As we show in the first example, it's there's a direct way to do that within the setup, with the same setup that Massimo described as well. Massimo referred to different models and the like, but there's no reason why those each model couldn't be indexed by a different parameter, and one can treat the parameter ambiguity in the just like going across models. In fact, what the distinction is between a model and a parameter is blurred anyway in many contexts. But yes.
May I just ask one follow-up question? So I understand that the question was just more like in the first example. Then, how do you get the size of the ambiguity set for each individual parameter?
Yeah. So there's different ways to do it. The way that we chose to do it in this paper was to look at was again appeal to relative entropy, but it was it was a kind of the implied local evolution of relative entropy that we use there in order to constrain. So constrain all the models in question to have the same relative entropy, but it did more because it was constraining the local evolution of it, and that gave us rectangularity. But there's no reason why that. I mean, we found it convenient because we were using relative entropy for model specification too. But there's nothing that really ties our hand on that point.
Thank you.
One could do explicit robust learning, right? One could have a bunch of, one could talk about doing counterparts to things like families of priors and posteriors and update posteriors and have dynamic learning taking place and watch, and perhaps even let sets, contract on you as you gain more information.
Thank you, Lars, again for your talk.